I'm absolutely delighted to be here at the University of Brasília. So let's just start with one of the simplest of machines, the wheel. And this particular example goes back many, many thousands of years. But I'm not going to talk about the wheel in any detail because we know how important it is. But I'm going to touch on steam engines, on electric motors, on internal combustion engines, on diesel engines, on jet engines, on rockets, on our own biological motors, which have been around for a long, long time, longer than any of these artificial machines. And then those that are close to my heart, molecular artificial machines. And by no means is this the end of the story. We can look to the future, and these gaps have to be filled in. So if we start by looking at steam engines, then the bottom left-hand corner shows one that was brought into being by fellow Scot, James Watt, back in 1765. This one, in 1883, was used in the northern parts of Pennsylvania in the United States to pump oil. And then, quite soon afterwards, these engines took to rails. And you see up in the top right-hand corner a very famous locomotive. It's the Stephenson rocket. And if you go to the Science Museum in London, you can feast your eyes on this 1829, this is where steam engine on wheels. Let's now look at further advances in that era. Here is an example of the Flying Scotsman, which allowed the journey between London and Edinburgh, where I was born, in Scotland, to take place in 6 hours. This was transformative at the time. And here is an example of a steam engine that is still used today in Oregon for tourists to be able to go around that state and enjoy the scenery. Electric motors. Well, here is a device that was first devised by Michael Faraday that shows how to transfer electric energy into motion. Here is the first electric motor that was invented by a Hungarian, János Jedlik, back in 1827. Here is an example of an electric motor. It was a gift of James Joule to Lord Kelvin back in 1842. But it was about half a century later before the first hair dryers came on the scene. And now, of course, we have electric cars. And in addition to having electric cars, if you go to China, you find that they have a transport system that connects 60 cities the size of New York. It happened very, very quickly by high-speed rail.
To Shanghai, high-speed train has even clocked in speeds up to 480 kilometers an hour. That's about 300 miles an hour.
Awesome, absolutely awesome. If we come to the internal combustion engine, then here is an early patent by von Langen, a German engineer, that within a very short period of time found its way into cars. And here is the first one that was available to the masses in America. About 17.5 million of these Ford T's were sold between 1908 and 1928. And in more recent times, here is my own Toyota Corolla. And what is interesting, once you win a Nobel Prize, you immediately get a special place to park your car. Diesel engines. So I learned putting this talk together that it comes from the name of Rudolf Diesel, a German who invented the first diesel engine back in 1893. And nowadays, these diesel engines are used to power big cargo ships that are moving across our oceans. If we now turn to jet engines, then British inventor Sir Frank Whittle, whose name is inexorably linked to their discovery, invention, if you like, gives us a situation where nowadays, and here you see taking off is an F-22 fighter, and at the same time, you see landing at London Heathrow a Boeing 787, a Dreamliner, having made the journey from Perth in Australia, some 9,000 miles, non-stop in 17 hours. Just absolutely incredible. Now, here's something that will interest you, I hope. At any one instance in time, there are 12,000 of these contraptions in the air. And if we put 200, 250 people in each, there are 2.5 million. There is the population of Brasília, not on land here, but up in the air. Think about it. Amazing. Rocket engines. So they came into being rather sadly during a war. But in more recent times, in 1969, we had the first landing on the moon by Bud Aldrin and Neil Armstrong. And then very close to me is the fact that a young student, Helen Sharman, was the first student or first astronaut to be put into space, courtesy of the Russian Cosmos event. All right, so now I want to just step back and look at biological motors for a minute. So here is the system that allows us to move our muscles, actin and myosin. But they have to be powered by another rotary motor. So the first one is a linear one, and the second one is a rotary one, which takes adenosine triphosphate and phosphate and makes adenosine triphosphate. And this is the chemical, as it were, store of energy in our bodies. And all of us, adults in the audience, are creating up to 40 kilograms of adenosine triphosphate every day. Now, it doesn't become a huge burden because as we create it, we use it in flexing our muscles and so forth. But if we're a sports person, then we will create our body weight of ATP each day. So here we see Serena Williams at Wimbledon back in 2016, winning the women's singles. And then, no guessing who I pick for the male, Scott Andy Murray, again in 2016, winning the men's final. And both of them producing enormous amounts of adenosine triphosphate in order to accomplish these feats. Let's go back to molecules. So I'm going to be talking today about a particular type of molecule that has mechanical bonds to it. We call them mechanically interlocked molecules, or MIMs for short. And they're made by using the recognition between molecules. The stickiness that brings them together makes them self-assemble, and this all happens under the direction of a template. And along the bottom you see a complex. We call this a pseudorotaxane. And with a little imagination you can see how two big stoppers can come on and we make something called a rotaxane. Or we just take the blue linear part of the pseudorotaxane and tweak it into a circle and we have a catenane. So my roadmap today is going to be the following. We're going to look at 35 years of a research summary that has led to molecular machines. And we may, if time permits, look at radical recognition and how it has led to molecular pumps. We'll look at joule pumps very, very briefly, and I'll say a thing or two about the nature of the mechanical bond, and if time permits, something about engines, timelines, and reflections. All right, so let's start with the 35 years of summary. It started for me when I was out of academia for 3 years at Imperial Chemical Industries Corporate Laboratory in Cheshire in the UK. And it was there, believe it or not, that I fell in love with a weed killer, Paraquat, also called methyl-viologen. It's a highly deficient source of electrons in an aromatic setting. And I paint it blue. And it falls in love with anything that is pi-electron rich. For example, this naphthalene derivative, 1,5-dimethoxynaphthalene. And the outcome is that red likes blue, and blue likes red. And we use this principle to build, in the first place, a large macrocycle. We call it bisparaphenoline 34 crown 10, or BPP 34C10 for short. And here you see in the top right-hand corner an X-ray crystal structure in a space-filling format of that ring system. And you can see how if we present it with Paraquat, the Paraquat gets trapped inside in a very, very suggestive manner. If I take my fingers and form a ring, the Paraquat is pointing through like that. And when you see that image, you already see we're well on the way to making a mechanical bond. We just have to put large stoppers on the end, or we create another ring system, which is on the right-hand side, which is a blue component built up of 2 Paraquat units linked by paraxylene units. And no surprise, red units like to go inside this particular blue unit. So we can put, by 1987, blue inside red, and by 1988, red inside blue. So we're poised, ready to make catenanes and retaxanes. So here's a movie just to perhaps animate what I'm talking about. Here is Paraquat. Methyl-viologen is the other name for this compound, finding a home inside this red macrocycle. So we can put blue inside red. Let's turn it round, and we have what we call the little blue box. And we can put red, things that love this blue box, inside the blue box. But the blue box is not easy to make because it's very, very highly strained. And so we make it in the presence of a template, which we then remove afterwards. Now, if we, instead of having a string with red on it, we have a ring. And there it is on the right-hand side. I call it a template. This is BPP 34 crown 10. And we have the constituents to make the blue box up in the left-hand corner. They don't talk to each other. But as soon as a covalent bond is formed between a nitrogen and a carbon atom with the loss of a bromide, we get essentially a derivative of the Paraquat. And we know that it wants to live inside this red ring. And so it worms its way inside. And these vertical lines show that it is finding weak interactions, but nonetheless important interactions to hold that thread in that ring. And we just need to close another nitrogen-carbon bond, which is the next thing that happens, and we have a mechanically interlocked molecule. We have a 2-catenane. And amazingly, it was delivered to us in the first reaction. This doesn't happen very often in a 70% yield. Nowadays, we can make it quantitatively. And what was even more stunning was when we saw the picture from X-ray crystallography of how the rings were placed with each other, we realized that we were into a very, very exciting period, because in that picture, on that front cover of Angewandte Chemie, you can see from the blue component up in the northeast down to the red one in the southwest, blue, red, separated by 3.5 angstroms. This is the same separation distance that our bases have in our DNA. So there's nothing so different between the artificial world and the natural world. We're using the same weak interactions. And so here's a movie that shows how these components come together and finally close that carbon-nitrogen bond, and we have a 2-catenane. So once this is made, it is rich in relative movements. The fastest one, that's occurring about 2 million times a second, is a rocking motion of the red ring with respect to the plane of the blue ring. The second one, which is a little slower, occurring about 1,000 times a second, and it can be clockwise or anti-clockwise. I call it pirouetting. It's the second one. The third one, which is the slowest one of all, happening about 30 times a second, and these are all numbers at room temperature, is the circumrotation of the red ring through the blue ring. So after we had made a 2-catenane and revealed its potential, we next made a 2-rotaxane. And here on the right-hand side, you see the template, the dumbbell component that I've drawn in a very appropriate way in order for the same chemistry that we saw in making the catenane to be formed to be used to form a 2-rotaxane. Now, it doesn't happen so efficiently because this dumbbell, although I draw it like that, is waving around, and it's not so pre-organized and therefore not so liable to give a good outcome. But nonetheless, at 32% on a first trial, that was a good delivery. And so again, I show the movie that shows how the linear component is trapped within the ring, and we've made our first rotaxane. Now let me redraw this in a linear way. And what you're looking at here is what we call the molecular shuttle. This blue ring, which is on this red station, as I might call it that, on the left-hand side, moves to the one on the right-hand side, and it moves back and forward. And this is happening about 2,000 times a second. So this is the first example of a potential or prototype of a linear motor. And you can see this in this movie, how the ring moves back and forward between these two red stations. Now, if we replace two identical stations with two different ones, so we make a bigger red one and one that is green. And the one that is green, which is called benzidine, likes the blue better than the red. And so at room temperature, it spends 84% of its time on the green, the blue ring, and only 16% on the red. So this is what we call a non-degenerate molecular shuttle. And so again, the movie shows that it spends little time on the red and a lot of time on the green. But we can take this particular system to the next stage because we can speak to the green unit. We can speak either electrochemically, which I don't show here, or we can add some acid. And if we add some acid, the protons will be attached to the nitrogens, and they will become positively charged. And then Coulomb's law of physics comes into being and tells the ring, leave the green, go to the red, and of course the green becomes a different color, this sort of brown color. So here is the movie showing the molecular switch in action, how it will spend a lot of its time on the red, provided the green has been protonated and been given a positive charge. So that was the beginning of the 35 years of research summary. The next part that I want to mention involves radicals, and I want to just introduce, because I want to get over here that increasingly as my career has unfolded, it's not about me, it's about the students that's worked with me. It's about us, it's about them. And one of these people is this man, Ali Trabulsi, who came from Lebanon. He got his PhD degree in Strasbourg in France before joining me at UCLA and then moving to Northwestern University. And by this time, I was giving my students and postdocs a huge amount of freedom. And he carried out an experiment that someone else in the group described as being intellectually disruptive. He asked himself, if I take the blue box that the Stoddart group have been playing around with for all these years and present it with Paraquat, is there a way by which I can get them to like each other? And yes, there was. If he used zinc dust and reduced the amount of charge and formed what we call radical cations, the outcome was we formed this tris-radical tricationic complex with very much stabilization. In terms of kilocalories per mole, 6 kilocalories per mole. It was a major breakthrough, and it allowed us to go on and make molecular machines. In the bottom left-hand corner, you see a crystal structure of this radical species. And what is more, and this is another story, it forms an infinite stack, and you have a very highly conducting material, which we have explored in other directions. So all I want to do here is to get the message across to the young people that get yourself into an environment where you have enough freedom to express your creativity, because that's what I've allowed many of my subsequent students, and I think you will see 13 or 14 of them here, to follow in the footsteps of Alex Trabulsi, who founded the Radical School in 2010 at Northwestern. So in the introducing of these radicals, as I say, we have this very, very strong complex of over 6 kilocalories per mole. And what we can do is that we can use it to form a so-called energy ratchet, so that we can bring a ring on to a pseudo-dumbbell. These dumbbells are equipped with stoppers that are not big enough to stop rings coming on. One is charged, and it's on the left-hand side in this diagram on the right, and the other is neutral. The neutral one is green. And if you carry out a reduction and then a relaxation process, followed by an oxidation and another relaxation process, you can move this ring from the left-hand side across to the right-hand side. And this is part of what you have to solve in order to be able to make a molecular machine. And so that allowed us to design a molecular pump where this diagram shows the making of it. So on the left-hand side of the long linear component, we have this part which is ready to accept the ring, provided we reduce the charge down from 6 overall positive charges to 3 and form this tris-radical tricationic complex. And then once we get it on there, if we oxidize, it'll want to and has to depart by the right-hand side. It has to go over a steric barrier. Sometimes I call it a speed bump. And when it goes over, it is trapped on a long chain. It's not lost into solution. And so the energy keeps rising in this system. We've made a molecular machine. Okay, so here's another movie that shows how the ring has come on, and it is purple when it comes on. Then when it's blue, it has been oxidized, and it goes over the speed bump. Purple, it comes on. The one that came on already wanted to come back. The speed bump stops it. The second one joins it. And so if we go through steps, we reduce, we oxidize, we heat, and we reduce, we oxidize, and we heat again. And we have 2 rings on this dumbbell. We've made a molecular pump. We've made a molecular machine. Okay, so here is the chemical constitution of this pump written across the top of this slide. And if you're asking what is the experimental evidence, it's obtained in solution by a technique called proton nuclear magnetic resonance. And we see this trace that one obtains after one cycle of reduction and oxidation, and you can see that the ring is sitting ready with some heat, and we're working at 42 degrees centigrade to pass over the speed bump onto the collecting chain. And these high field on the right-hand side signals tell us when it has all passed over the speed bump. It takes 1.5 hours to do this. And we can repeat it, and we can get the second ring on. And so now we have a molecular machine. And I use a movie just to get the message across. When it's purple, it brings the ring on. When it's blue, we have restored the positive charge. We use thermal energy to get it over the speed bump onto the collecting chain. We're going to bring the second one on now. It was purple, now it's blue, and it's going to, with thermal energy, make its way over the speed bump onto the collecting chain. So, in summary, we can pump one ring followed by two rings. And in doing this, we're doing chemistry away from equilibrium. Now, our biological motors are all working away from equilibrium. If they weren't, we wouldn't be sitting here as live human beings. It's very important that we look at systems that are pushing themselves away from equilibrium. And to summarize, that first ring comes on in 90% yield, and it crosses a barrier of 23 kilocalories per mole to get there, after a redox cycle involving reduction with zinc and oxidation with nitrosyl hexafluorophosphate. And if we repeat that whole process, the second ring comes on with 85% yield. Overall, the yield of the final free rataxane down in the bottom-hand corner is 77%. But the most interesting thing from this experiment is that the barrier for the second ring coming on is within experimental error at 23.1 kilocalories per mole, the same as the first one at 23.0. In other words, the presence of the first ring on the collecting chain is not inhibiting the passage over to get the second ring. And so if we go from here to a thought experiment, and this is further than we went in experimental terms, we can bring on, by reduction and oxidation, juggling about with energy barriers, one ring, and then we can repeat this whole process and notice how the energy landscape changes and how, as we bring on the third one, the level of the energy expression rises. So we bring on a fourth, and it continues to rise. And so the conclusion is that each cycle has trapped one ring in a very high energy state. Some of the energy input is trapped, some will have gone to heat, and finally, we can say work has been done. We've made a molecular machine. This leads to very interesting materials called entropically dominated polyrataxanes. Now, in the lab today will be people working on what we call joule pumps, with polymers in the middle, with these pumps on either end, and they'll be bringing rings on one after the other to, as it were, fill up all the spaces along a polymer chain. And there's very good reasons why we want to do that. There's good reasons in material science, there's good reasons in batteries and energy science. I'm not going to have time because of the clock to go there today. I just complete my story by saying now we're pumping rings onto polymers. They come on from each end. We've got molecular pumps. We've got machines that have been made artificially at each end. And you can see these rings being collected on this long polymer chain. So what I want to do is simply end with a summary where I define the icons that I'm going to use. I'm not going to be talking. You're going to be listening to a video with some music. And when you see a padlock with a key outside, molecular recognition is switched off. When the key is in the lock, it is switched on. And remember the interaction between red and blue. That is what we call donor-acceptor recognition. We'll also have templation, and I use this symbol here. These are the symbols that we used to use before we had sophisticated ways of drawing chemical structures with computers, called ChemDraw. We used to have these templates to draw ring systems by hand. So that's the icon I use for templation. And then you saw how important the radical recognition became in the design of the molecular pump, and the fact that when the radicals are featuring, we have a purple system. We will use heat, and we will also use electricity. We'll use redox control, minus volts, plus volts, and we'll sometimes see ratios, which you saw with the non-degenerate molecular shuttle of 4:1, and then how you can chain switching with acid and base. So at this stage, I'm going to close with a video that will, I hope, leave you with a summary of what I've talked about, and hopefully I managed to get my message across. So please enjoy.
Ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien. Balayer, oublier. Je me fous du passé, avec mes souvenirs. J'ai allumé le feu, mes chagrins, mes plaisirs. Je n'ai plus besoin de balayer les amours, avec leur trémolo, balayer pour toujours. Je repars à zéro. Non, rien de rien. Non, je ne regrette rien. Ni le bien qu'on m'a fait, ni le mal. Tout ça m'est bien égal. Rien de rien. Non, je ne regrette rien. Car ma vie, car mes joies, aujourd'hui, ça commence avec toi. Non, rien de rien. Non, je ne regrette rien. Ni le bien qu'on m'a fait, ni le mal. Tout ça m'est bien égal. Non, rien de rien. Non, je ne regrette rien. C'est payé, balayer, oublier. Je me fous du passé, chagrins, mes plaisirs, je n'ai plus besoin de balayer les amours avec leur trémolo, balayer pour toujours, je repars à zéro. Non, rien de rien, non, je ne regrette rien, ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien, non, je ne regrette rien, car ma vie, car mes joies, aujourd'hui, ça commence avec toi.
Take a bow. Come on. Thank you.
We don't need to do anything else. We could just sit here and enjoy the dance, really. I mean, it was just, that was beautiful. We have a little time for question and answer. And please, I encourage you to use the time to ask questions. I would just like to start, though, by saying, you showed all these pictures of this lovely, diverse group of young people in your lecture, and then you just showed us how social science can be.
Yes.
I guess that must be such a source of pleasure, just having this wonderful diversity of people coming through the lab all the time.
Yes, Adam, it is what has made my life so enjoyable. I would almost say that it has displaced my and our, because it has been a team effort, achievements in research. The opportunity to get together over 50 years with over 500 young people, some of the smartest in the planet, and they certainly have come from Brazil as well as other countries, has been an enormous privilege. So 50 different nationalities from 50 different countries and 500. I've really been very fortunate. It's an enormously big family, and when I go to airports now, very often there are quite a few of these ex-family members there to greet me. It's very moving.
How can molecular machines be applied in industry or in our daily lives?
So they've already found application in material science. Some Japanese workers have used these polymers that I've been showing you, where rings slide back and forth, and they call them slide ring polymers. And they're already being coated in Japan on the back of cell phones. And the reason that they are being coated on the back is that if the material is scratched, then in front of your very eyes, the scratch will fill up. And this is because the rings on the polymer can move, and in moving, make the material scratch resistant. That's one example. Another example that has been published recently using the same kind of slide ring polymers is to increase the efficiency of lithium-ion batteries by inhibiting the coalescing in the battery medium of silicon nanoparticles, again because of the movement of the ring system. So we already see in the materials field applications. And I should perhaps have said first of all that there are very major applications back into chemistry itself. So the area of what we call stereochemistry has been revolutionized by the discovery of and invention of the mechanical bond. In the future, we will see big applications, I predict, in the health sciences.
Thank you. Thank you very much. Question right at the back.
eu penso que o professor Christian Hans Ørsted foi dos que fez também, tentou provar que eletricidade não interagia com o magnetismo.
It was just a comment to say that there was an earlier demonstration
Yes.
of electricity and magnetism.
Oh, all right. Well,
I think she was saying Professor Christian Hans.
all right.
I wonder if that was Hans Christian Andersen. I'm not sure. Please, go ahead. Your question, please.
Which properties do you look at when designing the molecular machine? For instance, I imagine that the ratchet could be used in signal transmission. So do you have any computational chemists helping you in the design?
I am sorry, you're going to have to repeat that a little bit more slowly, just the question.
Sorry. So which properties do you look at when designing molecular machines? For instance, I believe that the ratchets could be used in signal transmission. So do you have a computational chemist helping you in your group with the design?
Did you get that? I did. So it's,
Yes.
which properties do you look at
Yes.
when designing a molecular machine? For instance, with ratchaxanes,
Yes.
and there's a potential relationship to signal transmission. Do you have a computational chemist working with you?
Oh, yes. We work collaboratively with Bill Goddard at Caltech, internationally recognized computational chemist, and he runs a very big group of 70 or 80 people. So we work very closely with computational chemists. We do some computation ourselves, but we don't pretend to be, the world's best. And so if you're in that position, you seek the collaboration of the people you consider to be the intellectual leaders in the field. So yes, we do use computational chemistry.
All those times in machine development bring approaches and procedures. Which would be the challenges that people coming from mechanics and electricity, those other fields faces in developing a new approach in nanotechnology, or which challenges you face when you have to come to work with those people coming from these other fields.
Did you get the question? Is in order to do these things, you have to work with chemists, with people coming from different fields.
Yes,
what
yes.
are the challenges of working across the boundaries between scientific fields?
Yeah. Well, this is an excellent opportunity for me to state that I think the advent of nanotechnology, which I would give the credit in large measure to the physicists who in the late 80s brought scanning tunneling microscopes and atomic force microscopes into being, the group at IBM in Zurich. And of course this was recognized by, quite appropriately, a Nobel Prize. Also, I would say that the development of what became known, thanks to Jean-Marie Lane, 1987 laureate in chemistry of supramolecular chemistry. These two developments, one in chemistry and one in physics, I think, made it possible for nanotechnology to become a uniting force across physics and chemistry, and to also quite naturally embrace biology and engineering. And so what has been one of the big thrills of my academic life is to watch how we went from being very much in silos, in boxes, and not talking to each other, if I go back to the 70s and maybe the early 80s, to the time that we find ourselves in today, where I would say there is largely a seamless interaction between scientists brought about under the umbrella, I would say, of nanotechnology, across the spectrum from wherever you want to start, biology, chemistry, physics, material science, materials engineering.
Thank you very much indeed. Okay, so we have a question up here and then one down here, please.
Bom dia. Antes de tudo, gostaria de agradecer por compartilhar um pouco da sua pesquisa. Eu gostaria de saber, uma pergunta bem simples e talvez um pouco pertinente ao assunto, mas eu gostaria de saber qual é a origem dessa força invisível que faz os motores biológicos no nível molecular se movimentarem. E qual a sua origem? E por que elas agem de modo tão inteligente nesse processo de movimentação?
Straightforward question. What is the force that moves the molecular machines?
It is there naturally. These are very small entities. These are small molecules. And so they are subject to what we often call Brownian motion. And so it's not a question of making the parts move. It's a question of controlling their movement so that you dampen down movements that are already there. And so if I take the molecular shuttle as an example, I may portray it in pictures as being discrete, a ring moving from there to there. But really, what it's doing, this ring, is going back and forward like that on one station, then back and forward like this on the other station. And so what we do is look at a situation where the molecules are almost living in the face of a hurricane, and we need to dampen down that movement in order to be able to control it and then use it. So the movement situation is a given because of the laws of physics.
Sir Stoddart, congratulations for your brilliant presentation. I'm Felipe from the Brazilian Ministry of Science, Technology and Innovation, and our department is in charge of public policies for nanotechnology. So in terms of public policies, what are your advices to us in order to incorporate in our national strategy for nanotechnology? Thank you.
He's from the ministry, and it's the question of what is your advice for science policy for Brazil?
I have a very strong message to deliver here. The last 60 years, and it was enshrined by the scientific advisor to Franklin D. Roosevelt in 1945 after World War II. He made the point, and this was the basis for the formation of the National Science Foundation in the United States, that the best way to look for advancement in science was to fund people rather than to focus your money onto projects that were somehow perceived by often not front-rank scientists, not people who are working at the cutting edges, and therefore taking the people away from the freedom to be able to express their creativity. And I speak from the heart because for these last 10 plus years, I have run a research group with a huge amount of freedom. We have made two serendipitous, when I say we, two people within that cohort have made two serendipitous discoveries, and we now have two startup companies as a result of giving the freedom to the researchers to be creative and to do their own thing. This will always win out over very highly directed research, wherever it comes from, in my humble opinion. And I've often said the nation state that resorts back to supporting people rather than projects will have many Nobel Laureates.
We have three questions coming. First one here, please. Yes? Okay, you're going to be put on the spot by a 10-year-old here.
Yeah, absolutely. Thank you, Jose. I want to hear the question, though.
Can your nano machines bring an end to diseases such as cancer?
I would not want to make such an outrageous claim that it would bring the end of diseases that are seen to be the degenerative diseases like cancers and Alzheimer's and Parkinson's and so forth. I think these are very, very big challenges that face the human race. The solutions are not going to be the magic bullet that we saw almost 50, 60, 70 years ago when antibiotics were brought into our lives and saved, of course, many, many lives. And I always illustrate the advent of antibiotics by saying, if you're sitting in an audience like this, look to the person on your right and the person on your left. And prior to the advent of penicillin and its followers, these two people would not be there. So that was transformative. I don't see that immediately happening in the context of the degenerative diseases. I think the challenge is very much bigger. I speak from the heart, Jose. I lost my own wife from breast cancer after a 12-year battle. And whatever anyone says, the treatment is still, and I will be very blunt here, almost medieval. It is slash, burn, and poison. That is surgery, radiation, and chemotherapy. And we need to advance beyond that point. And I'm sure that the people here in the pharmaceutical industry, particularly those from AstraZeneca, are probably pursuing new ways and all power to their elbows in order to address these degenerative diseases. But remember, they come into being because we're all living much older. And you have got to ask yourself, have we the right to be able to live longer and longer? We already have a problem with population growth on the planet. And there are many, many questions, I think, that your question raises, other than just directly saying, yes, molecular machines are going to solve it all. No, they're not. They're going to play a part, but it's going to take a lot more, and many people working collaboratively to solve these major problems.
Question here, please.
And for letting us see a Nobel Prize dancing in front of us. That was very brilliant. My question is complementary to my young colleague here. In the presence of AstraZeneca, which is one of the big pharmas, we start thinking, what should we expect from these molecular engines in the medical field in the future? Would it be nano-sized surgeons?
What was the surgeons?
What should we expect from will it be nano-sized surgeons?
Yes, I think that is a good phrase. I would dream, and I have to emphasize this is dreaming, of development where these artificial machines would, to use your terminology, be small surgeons. I would say molecular prosthetics. And so just as we've gone through a time in the last 50 years where we can transplant hearts and kidneys and livers, and we can replace hip joints and knees and so forth, we're going to be working, I think, medically at a much smaller level with these nanomachines, which are going to be able, given enough time and enough development, to address the attack on cells, and particularly, of course, disease cells. So it'll be a much more active way of bringing about drug delivery than we know at present. I'm not saying there isn't, it's all passive, but the fact that we will be able to use almost little mini propellers to drill through cell walls, I think that could be transformative in terms of the treatment of degenerative diseases, coming back to the question that we had from Jose.
Okay. Oh gosh, all the questions are coming now. We haven't got very long. Quick questions. Then you. Okay, 3 more, I can see. Quickly.
All right. I would like to ask because you've been researching this for 35 years, which evidently is a lot of time. I would like to ask you, when you started the research in the 80s, did you already see the deep theoretical ramifications that it would have, and then also the practical applications? Did you already see that in the 80s, or it became more evident as the research developed?
Oh, very quickly, I did not see what was coming. I never claimed to be able to see very much beyond 18 months ahead. And even then, I would be pushing it. You know, it's much more an incremental process. You have to undergo, as you start out at university, at least 10 years, 10,000 hours of an apprenticeship to get to be familiar with the particular science that you decide to, or engineering or whatever, to focus your attention on. And after that, or while that's happening, you start to think about what is the big problem that I might address that, if I were successful, will be a contribution to science and a contribution to humanity. You really have to ask yourself that question. Too many people put it off or never ask it, and they continue to follow the footsteps and go down the beaten tracks of others, yeah? So it is absolutely important that you ask yourself, is there a big problem out there? If you identify it, get involved in some risk-taking and address it.
Thank you. Thank you. Last two questions, but here, quickly, please. Oh, where's the microphone gone? And then there's one. Okay, sorry, you had one. I'm sorry. Okay.
So first of all, I would like to thank you, sir, to be here. It's an honor. It's a great, really big honor. So I study aerospace engineer here in Brasília University, and one of the major problems we have, it's about to carry weight into space. And we are coming to in 2021, and so to go to Mars. And I would like to know if you, sir, have any perspective of your molecular engines into the aerospace industry use.
I think we're not on the same level in terms of scale. So forgive me being negative, but I don't immediately see an application for nanomachines in terms of space exploration, if we're talking about the bread and butter of getting rockets up into space. Of course, if we're talking about what happens inside a space craft or a space capsule, then, well, surely there'll be human beings there, and then we'll be discussing that there may well be something that relates to their diets or their health or whatever, where these artificial machines can play a part. So that's about all I think I can say.
Taking his question another way, would you like to go to Mars?
I think I will pass on that, yeah.
Question here. Please, lady here.
Yes.
Congratulations for your wonderful talk. Which advices, which take-home message would you give for young students and young scientists to not give up science?
So she wants a take-home message.
It's a good, perfect last question.
Yeah, yeah.
A take-home message for young scientists to encourage them not to give up science.
Yeah. Okay, so you have to be, I think, engaged at a level of enormous emotion and passion. You know, I was an only child, and I think to some extent I was given the opportunity, being brought up also in the countryside, to dream about what I might do with my life. And as I zeroed in on science, these dreams continued. And whatever comes in your path that may be presenting a difficulty, your dreams have got to be such that they propel you on in an optimistic way, if you'll excuse the phrase, come hell or high water, that nothing will stop you. You have to be driven. You know, after my first taste of doing research in a laboratory in 1963, when I was 21 years of age, it didn't become something that I liked. It became an addiction. I could not take myself away from the laboratory in the evening, and I couldn't get back to it sooner in the morning. And that passion has existed for the remaining 55 or 60 years. Maybe not the laboratory, but to get back to my office and to be beside the young people just by walking a few steps along to the laboratory. And I'm very lucky to be able to interact with these wonderful people between 18 and 32, who are some of the brightest on the planet. And so, however you look at it, and it changes in its pattern as you live your life, there is so much in the way of enjoyment. There's so much in the way of absolute fun to have, just from committing yourself in a passionate way to the level of addiction to science.
Thank you very much indeed, Fraser, for taking time away from the lab to share your passion with us all. Thank you.